My name is Yedla Akshay Babu. I am a second year undergraduate student of the Department of Ocean Engineering and Naval Architecture. My roll number is 22NA 30035. Synthesis of lifting flow over a circular cylinder. Consider the flow synthesized by the addition of the non-lifting flow over a cylinder and a vortex of strength gamma, as shown in the figure. Combining non-lifting flow over the cylinder and vortex of strength gamma gives us the lifting flow over a cylinder. For non-lifting flow over a cylinder of radius r, psi 1 is V infinity r sin theta into 1 minus r square by r square. The stream function for a vortex of strength gamma is given by psi 2 is equal to gamma by 2 pi ln of r plus some constant. The value of the constant is arbitrary. So let the constant be minus gamma by 2 pi ln r. Combining the equations gives us psi 2 as gamma by 2 pi ln of small r by capital R. Now the resulting stream function for the flow is psi is equal to psi 1 plus psi 2. Psi is equal to V infinity r sin theta into 1 minus r square by r square plus gamma by 2 pi ln of small r by capital R. Now if small r is equal to capital R, then psi becomes 0 for all values of theta. Since psi is constant in the equation of a streamline, small r is equal to capital R is therefore a streamline of the flow. But small r is equal to capital R is the equation of a circle of radius r. Hence the equation is a valid stream function for the envisaged incompressible flow over a circular cylinder of radius r. Note that the streamlines are no longer symmetrical about the horizontal axis through the point O, and the cylinder will experience a resulting finite normal force. However, the streamlines are symmetrical about the vertical axis through this O, and as a result the drag will be 0, as we prove shortly. Now for non-lifting flow over a cylinder of radius r, the equations for vortex flow we have for the lifting flow over a cylinder of radius r, Vr is equal to 1 minus r square by r square V infinity cos theta, and V theta is given by minus of 1 plus r square by r square V infinity sin theta minus gamma by 2 pi r. To locate the stagnation points in the flow, set Vr is equal to V theta is equal to 0. Now small r is equal to capital R from the above equation, and substituting small r is equal to capital R in the V theta equation, we get theta is equal to arc sine of minus gamma by 4 pi V infinity r. Since gamma is a positive number from equation, theta must be in the third and fourth quadrants. That is, there can be two stagnation points on the bottom half of the circular cylinder as shown by points 1 and 2. These points are located at r and theta, where theta is given by the equation. However, this result is valid only when gamma by 4 pi V infinity r is less than 1. If gamma by 4 pi V infinity r is greater than 1, then equation has no meaning. If gamma by 4 pi V infinity r is equal to 1, there is only one stagnation point on the surface of the cylinder, namely the point r and negative pi by 2. Now solving for r, we have small r is equal to gamma by 4 pi V infinity plus or minus square root of gamma by 4 pi V infinity square minus r square. Hence, for gamma by 4 pi V infinity r greater than 1, there are two stagnation points. The velocity on the surface of the cylinder is V is equal to V theta is equal to minus 2 V infinity sin theta minus gamma by 2 pi r. In turn, the pressure coefficient is obtained by substituting the equations. Cp is equal to 1 minus V by V infinity squared, or Cp is equal to 1 minus 4 sin square theta plus 2 gamma sin theta by 4 r V infinity plus gamma by 2 pi r V infinity square. For inviscid flow, Cf is equal to 0. Hence, the drag coefficient is given by Cd is equal to Ca is equal to 1 by C integral Le to Te Cpu minus Cpl dy. And converting into polar coordinates, we have y is equal to r sin theta and dy is equal to r cos theta d theta. And noting that C is equal to 2r, we have Cd is equal to 1 by 2 integral pi to 0 Cpu cos theta d theta minus 1 by 2 integral pi to 2 pi Cpl cos theta d theta. The limits of integration are explained as in the first integral we are integrating from the leading edge, meaning over the top surface of the cylinder. Hence theta is equal to pi at the leading edge. And moving over the top surface decreases to 0 at the trailing edge. In the second integral, we are integrating from the leading edge to the trailing edge while moving over the bottom surface of the cylinder. Hence theta is equal to pi at the leading edge, and moving over the bottom surface increases to 2 pi at the trailing edge. Cd is equal to minus 1 by 2 integral 0 to pi Cp cos theta d theta minus 1 by 2 integral pi to 2 pi Cp cos theta d theta. When doing the calculations, we obtain Cd is equal to 0. So these equations confirms our intuitive statements made earlier. The drag on a cylinder in an inviscid incompressible flow is 0, regardless of whether or not the flow has circulation about the cylinder. With Cf is equal to 0, we have Cl is equal to Cn is equal to 1 by C integral 0 to C Cpl dx minus 1 by C integral 0 to C Cpu dx. And again converting and doing the calculations, finally we obtain Cl is equal to T by Rv infinity. Now from the definition of Cl, the lift per unit span L dash can be obtained from L dash is equal to Q infinity SCl is equal to 1 by 2 rho infinity V infinity square SCl. So we have L dash is equal to rho infinity V infinity gamma. This equation gives the lift per unit span for a circular cylinder with circulation gamma. It is a remarkably simple result, and it states that the lift per unit span is directly proportional to circulation. The production of zero drag is totally erroneous. Viscous effects cause skin friction and flow separation, which always produce a finite drag. The inviscid flow treated in this chapter simply does not model the proper physics for drag calculations. The general ideas discussed above concerning the generation of lift on a spinning circular cylinder in a wind tunnel also apply to a spinning sphere. This explains why a baseball pitcher can throw a curve and how a golfer can hit a hook or slice, all of which are due to non-symmetric force about the spinning bodies, and hence the generation of an aerodynamic force perpendicular to the body's angular velocity vector. This phenomenon is called the Magnus effect, named after the German engineer. These flow field pictures were obtained in water where aluminum fillings were scattered on the surface to show the direction of the streamlines. Magnus effect is not employed for powered flight. On the other hand, in the 1920s, German engineer Anton Flettner replaced the sail on a boat with a rotating circular cylinder with its axis vertical to the deck. In combination with the wind, this spinning cylinder provided propulsion for the boat. Moreover, by the action of two cylinders in tandem, and rotating in opposite directions. Flettner was able to turn the boat around. Now coming to one example problem. Consider the lifting flow over a circular cylinder. The lift coefficient is 5. Calculate the peak pressure coefficient. Now note that the maximum velocity for the non-lifting flow over a cylinder is 2v infinity, and that it occurs at the top and bottom points on the cylinder. And when the vortex is added to the flow field, the direction of the vortex velocity is in the same direction as the flow on the top of the cylinder, but opposes the flow on the bottom of the cylinder. Hence, the maximum velocity for the lifting case occurs at the top of the cylinder and is equal to the sum of the non-lifting value minus 2v infinity and the vortex minus gamma by 2 pi r. So hence v is equal to minus 2 v infinity minus gamma by 2 pi r. The lift coefficient and gamma are related through the equation CL is equal to gamma by RV infinity is equal to 5 given in the question. So gamma by R is equal to 5 V infinity and V is equal to minus 2 V infinity minus 5 by 2 pi times V infinity. So solving it gives us minus 2.796 V infinity. Substituting these into the above equation, we obtain Cp is equal to 1 minus V by V infinity square is equal to 1 minus 2.796 square, which is equal to minus 6.82. Thank you.